systems of non-linear equations, which was 5-5, and now 5-4, and now 5-5. And today is the 20th. 5-5, systems of inequalities. We will start with a simple example with linear inequalities that you have seen before, and then we'll look at the other ones. Okay, so here's an example, number 30, on page 600, and that is 2x minus y less than or equal to 4, and the other one is 3x plus 2y greater than negative 6. Obviously, this is not a system of equations. It's a system of inequalities. 2x minus y less than or equal to 4, 3x plus 2y greater than negative 6. So if you remember, the first step for this is to write the equation, the corresponding equation. I'm not changing the inequality into an equation, but I have to graph the equation first. And then I have to find two ordered pairs, and we always look for the x and y intercepts. When x is 0, I get y to be very good. So this is 0, negative 4, perfect. And then when y is 0, I get x to be very good. So then 2, 0. I will graph this line. And I have to graph 0, negative 4, and 2, 0. I stop, and I look at the inequality symbol. If it has the equal symbol, and it does, I will graph it as a solid curve, or line in this case. And I will write 2x minus y equals 4 on the line, below the line, but nowhere else, close to the line. I hope you remember this or see that this line divides the plane into two regions, the region below and the region above. I will pick the origin to check this region because 0, 0 is the easiest to work with. 0, 0, I get 0 less than or equal to 4. If you say that this is true, I will shade in the region that has that point. If you say no, this is false, then I will have to shade in the opposite region. Is this statement true?
Yes.
So then I will have to shade in. And all this, including points on the line, represent 2x minus y less than or equal to 4. The solutions, the ordered pairs that make this inequality true. I will repeat for the second one, in which I have 3x plus 2y equals negative 6. When x is 0, y is very good. So 0, negative 3. When y is 0, x is very good. Thank you. So negative 2, 0. I will plot these points, negative 2, 0, and 0, negative 3. But I have to stop and inspect the inequality symbol. It does not have the equal symbol. Therefore, I cannot draw this line as a solid line but remember to write 3x plus 2y equals negative 6. The reason is the points on this line will not be part of the solution. Now I see that this red line divides the plane into two regions. Also a remark. If the line passes through the origin, I cannot check using the origin. I have to pick another point, 10, 10, or whatever, but not the origin. Since it does not pass through the origin, I'm going to use the origin and ask myself if this is a true statement. If it is true, I will shade in the region that I checked by picking a point in that area. If it's false, then I will shade in the opposite. Is 0 greater than negative 6?
Yes.
Very good. So all this region, the red region, is 3x plus 2y greater than negative 6. Since this is a system of inequalities, I want both conditions to be fulfilled at the same time. I don't care about the second one or the first one. I care about the whole thing. Both conditions at the same time. In other words, I'm asking myself, do the green and the red territories, do they have any common area? Yes. Yes, they do. And here it is. Points on this line. Not points on this line, but very, very close. And everything in between. All this is both. So if I want ordered pairs that verify the entire system, I will have to pick them either on this line or anywhere in between, but not points on this line. So this was a linear. And now let's look at a couple nonlinear. This we've seen in the previous course at some point in time. Okay. So let's look at nonlinear now. 48, same page. 48, x squared plus y squared less than or equal to 4, and x plus y greater than 1. I see one linear and one nonlinear, another combo. Okay, so let's start with the first equation, x squared plus y squared equals 4. And I have to remember what this is. Circle. What is it? A circle. Very good. What is the center and what is the radius?
0, 0.
Very good. I don't subtract anything from x. I don't subtract anything from y. Awesome. So the radius is?
2.
2. Yes. I wanted to write r again. I don't know why. I stop and I ask myself, is it a solid curve? Yes or no? Yes. Yes. So here it is. It's not going to be perfect, but this, just this curve, is the equation. I did not graph the inequality yet. I see that this circle divides the entire plane into two regions, the inside and the outside. I'm going to check the inside with the origin again. And I get 0 less than or equal to 4. If you say this is true, I will shade in the inside. If you say this is false, I will shade in the outside. It is true. So all the inside, all points on the inside, including points on the circumference, represent solutions to this inequality. I will have to repeat now with x plus y equals 1. Any questions? Any questions? Are we okay? Okay, so then x plus y equals 1. When x is 0, how much is y?
0. 1.
Good. So 0, comma 1. When y is 0, how much is x? Good. 1, comma 0. Is that okay? Okay. So 1, comma 0 is here, and 0, comma 1 is here. I have to stop and check the inequality symbol. Is it a solid line or not? No. On the line, please write x plus y equals 1. We did not graph the inequality yet. I see it divides the entire plane into two regions. I check the bottom one with 0, 0. And I get 0 greater than 1. If you say it's true, I'll shade in this. If you say it's false, I shade in the opposite. False. False. I cannot take the region that has that point. I have to take the opposite region. So this is x plus y greater than 1. I don't want green, I don't want red. I want both. And they do overlap. Points on this curve, points very close to the line, and everything in between. Both. Any questions? Any questions?
Is that how we would show the answer?
That's the only way, yes. Whether we have no other way. I would not be able to tell you, hey, imagine a circle, and imagine that it's crossed by a line, and somewhere above the line there is a common area. I have to present all those. There's no other way. Very good. Let's look at one more that is nonlinear. Yes. Let's look at 46. And now if you ask, why do we do this? It's for linear programming. However, we removed linear programming from the course. Don't ask me why. Okay, 46. 46y greater than or equal to x squared minus 4, and x minus y greater than or equal to 2. We start with the first equation, y equals x squared minus 4. And I've seen this so many times that I'm dreaming about it now. What is it? Yes. And so from x squared, where do I move it?
Down 4.
Yes. Where will it cross the y-axis? At, of course, 0, -4, but where will it cross the x-axis? Okay, let's say why we don't know. So I have to set y equal to 0, which means x squared minus 4 equals 0. How many solutions?
2.
Exactly. X equals, when we move 4 and take the square root.
2 and -2.
Very good. Solid curve? Yes?
Yes.
Yes. We know it divides the entire plane into 2 regions, the inside and the outside. I will check with the origin again. 0 greater than or equal to -4. If you say true, I'll shade in the inside. If you say false, I shade in the outside.
It's true.
Yes. So first of all, this is y equals x squared minus 4. The inside is y greater than or equal to x squared minus 4, including points on the parabola. And then the next step is to do the same thing with x minus y equals 2. So x minus y equals 2. 2 ordered pairs when x is 0. Y is good. So 0, -2. And when y is 0, x is 2. 2, comma 0. I plot 0, comma -2. I plot 2, comma 0. Solid line or not?
Solid.
Mine is solid and shaky. Sorry. So x minus y equals 2. It divides the entire plane in 2 regions, top and bottom. I will check with the origin. 0, 0. 0 greater than or equal to 2. If you say yes, I'll shade in the upper part. If you say no, it's false, then I'll shade in the bottom. Yes. So this is x minus y greater than or equal to 2. Please do not write this on the equation, because it's not the equation. Okay, so I don't want green, I don't want red. I want both. So then this line, this curve, and everything in between. And that is both at the same time. Any questions? Any questions? Okay, so we are looking at 2 more sections before we start reviewing. One of the sections is 6.1, in which we will learn one method of solving systems that are linear, 3 equations, 3 variables. So 6.1, systems of 3 by 3. 3 by 3, we mean 3 linear equations in 3 variables. Systems of 3 by 3. Can we use substitution? Yes. Can we use elimination? Yes. But this is a different method. It uses matrices. Using matrices. Like before, when we look at the first example with a new method or function or whatever, it takes me like forever to explain because I talk a lot. But after we finish the first problem, then the rest will take much shorter. We'll go much faster. Okay, so I'm going to pick an example to illustrate. Okay, so let's say number 29 on page 631. After we do the first two problems, you can choose the next one. So x plus 2y, 29. X plus 2y equals z minus 1. X equals 4 plus y minus z. Let me check. Yes, 4 plus y minus z. And the last one is x plus y minus 3z equals negative 2. I'm checking now because sometimes I guess you know by now I copy from all sorts. Okay, I think I copied it correctly. Yes, it appears that it's correct. Okay, so first of all, this is a system. I see three equations, I see three variables, and they are linear equations. X, y, and z have power 1. Okay. Now, one thing that is not good, and it needs to be addressed, is the system is not arranged in the correct order to use this the matrix method. It's not clear, it's not arranged, it's not organized. All terms with x have to be one below the other. All terms with y, one below the other. All terms with z, one below the other. The equal symbol below the equal symbol, and the free term below the free term. So I will rearrange, writing x plus y minus z equals negative 1. X minus y plus z equals 4. And x plus y minus 3z equals negative 2. So this is the first condition. We cannot use this method of matrices if the system is not presented in the correct order. Then we have to define what is a matrix. A matrix is an array of numbers. The first thing we want to look at the matrix of the system, or the coefficient matrix. Matrix of the system, or called also the coefficient matrix, which is denoted by uppercase A, equal symbol, and two big brackets. And let's see what we have inside. The first column consists of coefficients of x, 1, 1, 1. The second column, coefficients of y, 2, negative 1, 1. The third column, negative 1, 1, negative 3. This is what we call the coefficient matrix. This column, if you want, of free terms is denoted by lowercase b. It is still a matrix, still has those big brackets, but it only has one column and 3 rows. Negative 1, 4, negative 2. Negative 1, 4, and negative 2. This is a matrix that is a 3 by 3, 3 rows, 3 columns, and this one is 3 by 1. Very good. So now the next step is the augmented matrix. What is the augmented matrix? It's a matrix that has A on this side of the vertical bar and has lowercase b on the other side of the vertical bar. The vertical bar basically represents the equal symbols. So here's how the augmented matrix looks like. I copy A, 1, 1, 1, to negative 1, 1, negative 1, 1, negative 3, vertical line, which is the equal symbols, negative 1, 4, negative 2. So this is so far just notation. We haven't done anything. So here's what if you show me this, and you don't show me anything else, and you just show me this, I know exactly what it represents. What it represents is this. X plus 2y minus z equals negative 1. X minus y plus z equals 4. And x plus y minus 3z equals negative 2. If you don't show me anything, I don't even need to know where it's coming from. I'll tell you what it is. Right? X plus 2y minus z equals negative 1, and so on and so forth. Okay. So the method we are going to use is called Gauss-Jordan method of solving the system. So here's what I want. I will apply some steps that we are going to talk about in a minute, and I would like the final form to look like this. Give me 3 numbers, any numbers you want.
1, 2, 3.
If I make the augmented matrix, there are a lot of steps in between that I didn't show. If I make that matrix look like this, I solve the system. How much is X?
1.
How much is Y?
2.
How much is Z?
3.
That's it. But how do I get that to look like this? The sequence of steps we're going to talk about right now. Of course, the answer is not this. I don't know the answer. But we just picked 3 numbers to illustrate that X plus equals 1, Y equals 2, Z equals 3. Okay, so how do I make that look like this? The sequence of steps is absolutely fixed, and we cannot deviate from it. If we try a different way or a different route, we will not solve the system. So what I want to get is this. Right? A number, a number, a number. So where do I start? What is the first step? What is the second step? And so on and so forth. Here it is. This is step 1. I have to get a 1 in the first column. First row, first column. Then my step 2 is to get the corresponding zeros underneath. Step 3 is this. Getting a 1 in the middle of column 2. Step 4 will be these 2. This will be step 4. What do you think step 5 will be?
1.
Exactly. Only this number in step 5 will allow me to get the zeros in step 6. We cannot deviate from this. One more time. 1, corresponding zeros. 1, corresponding zeros. 1, corresponding zeros. This must be the sequence. Okay. Now, what are the operations that are allowed here? And then we can start. There are only 3 allowed operations. Only 3 allowed operations. Number 1, number 2, and number 3. Okay, so I'm going back for a moment. Back to the augmented matrix. Here it is. Question for you. What if I take this row and put it here, and take this row and put it here? Will I change the solution of the system? No. I can change the order of the equations. It doesn't matter. If I consider equation 1, 2, 3, or equation 3, 2, 1, I will still get the same answer at the end. It doesn't matter the order I present them in the augmented matrix. Is that clear? So that's the first allowed operation. For whatever reason, I'm allowed to swap rows. I know each row is an equation, so I'm allowed to swap rows. Okay, number 2. Operation number 2. Am I allowed, for whatever reason, I decide to multiply here all the coefficients in this row by 3? Will I change the final solution of the system?
Just one row.
Well, any row.
No.
Will I change the system, the solution? No, absolutely not. I can always multiply both sides, any equation, by any number I want. The final solution will not change, as long as I don't multiply by 0, of course. So that's the second allowed operation. Multiply or divide any row by a non-zero number. Multiply or divide any row by a non-zero number. I cannot multiply by 0 and I cannot divide by 0. Any row. Okay, here's the last operation, but for the last operation, I would like to go back to this. I need an elimination example. Okay. Very good. Perfect example. So here in this system, last time we decided to eliminate x, correct? So we multiplied this row by -2. Negative 6x plus 14y equals negative 26, correct? And what did we do with this row? We added it to the next row. We added this row after we multiplied it by -3, and we added it to this row, and we got this equation. That's the third allowed operation. Multiplying any row by a non-zero number and adding the result to another row. One more time, this is what we did here. Let's go back for a second. We multiplied this row by -2, and the result, we added it to the second row to get a new equation. Okay? So that is the third allowed operation. Multiply, sorry, multiply any row by a non-zero number, and I'm not stopping here because that's number 2, and add the result to another row. Yes, I know, a lot of words. It sounds very complicated. It's not. Multiply any row by a non-zero number and add the result to any other row, to another row. Okay. Ready? I'm going to copy the augmented matrix. And this is 1, 1, 1, 2, negative 1, 1, negative 1, 1, negative 3, negative 1, 4, negative 2. Remember the sequence of steps. My first step is, and I got lucky, I want a 1 in here. It's already done. Good. My next step is I want a 0 here, and I want a 0 here. Do not put the equal symbol between matrices. This matrix will not equal the next matrix. The arrow means they're equivalent. So from here, I can write that, but they're not equal. Okay. So obviously, I will have to multiply row 1 by a quantity and add it to row 2, and also row 1 by a quantity and add it to row 3. So what do I multiply row 1 by and add the result here to get a 0? Yes. What do I multiply the entire row by to add the answer here and get a 0? I don't care about the rest. I just need a 0 here.
0.
Say it again.
0.
So if I multiply this by 0 and add it here, this will not change. -1. Right? It's the same with elimination. I need -1. And we cannot multiply by 0. Very good. So now, what would I multiply this row by so that when I add this quantity here, I get a 0 here? -1 again. So let's do this together, okay? Which row do I copy? Because it will not change. It's the row I'm using. I have to copy it. The row I'm using is row 1. This is the row I'm multiplying by -1, in this case, and -1 respectively. So that row cannot change. Let's do this together. 1 times -1 is
1.
plus 1. 2 times -1, -2 minus 1, -1 times -1, plus 1, -1 times -1, plus 4. We will repeat the same process for row 3 now. 1 times -1, plus 1. 2 times -1, plus 1. -1 times -1, minus 3. Awesome. 1 times -1, minus 2. What did we accomplish? This we accomplished. The first column is done. Where's my next step? So my first step was this. My second step is this. Where is my step 3? The 1. This one helped us with this. This one will help us with these. But well, how do I get a 1 here? Divide this row by. Yeah, but I don't really want to do that because I'm going to have -2/3 and -5/3. Is there another way? Keeping in mind that we have 3 possible operations. Swap rows, multiply or divide a row by a non-zero number, and the third one, which is the more sophisticated one, and multiply one row by a number and add the result to another row. But I want the 1 in here.
Swap
Yes, which ones?
the bottom one.
Exactly. And then multiply or divide by -1. Awesome. Because I want the 1 in here, and that's the easiest thing to do. Great. So then I want row 2 to become row 3, and row 3 to become row 2. Great job. Thank you. 1, 2, -1, -1. 0, -1, -2, -1. 0, -3, 2, 5. So all I did, I swapped row 3 and row 2. Now I still want the 1 in here. It's not ready yet. So what do I do, which is no problem, to this row to get a 1 in there?
Wait, what?
I need a 1, not a -1. So what will I do to this row?
Multiply by -1.
Yes, multiply or divide by -1. Same thing, very good. 1, 2, -1, -1, 0, 1, 2, 1, 0, -3, 2, 5. So what have I accomplished so far? Look what I have. Which row will I have to use now in order to get the corresponding 0 above 1 in the middle? Which row will I have to use?
Repeat the question.
Yes, which of these 3 rows, row 1, row 2, or row 3, will I have to use in order to multiply this by a number and add it here and get 0, multiply this by a number and add it here and get 0, because that's my next step. 0 here and 0 here. Which row will I have to use? It has to be 2, exactly. So row 2 gets multiplied by something and added to row 1. Also row 2 multiplied by something else and added to row 3. What do I need to multiply this number by and add it here to get a 0 instead of a 2? Perfect. What do I need to multiply this number and add it here and get a 0 instead of a -3? Which row do I have to copy now, which will not change because I'm using it? Perfect. 0, 1, 2, 1. Of course, if I destroy this, something is wrong. I can go back. What I have accomplished cannot change. If it changes, something is wrong. Okay. So 1 times -2 plus 2. 2 times -2 minus 1. 1 times -2 minus 1. Perfect. 1 times 3 minus 3. 2 times 3 plus 2. 1 times 3 plus 5. Great accomplishment. Where is my next step? Right here. In order to help us get the zeros. What do I have to do to this row to get a 1 here? Yes, row 3 divided by 8. Awesome. Are you with me?
With you now, when I go home, I'll be lost.
No, because we're going to have more examples in a minute. 1, 0, 0, 1, 0, 0. 1, 1, 2, 1, -5, -3. Do we already have one of the variables for sure? Which one? Z equals 1, indeed. We already know that. Perfect. Good. So now I need to multiply, obviously, this row by what to eliminate this? Perfect. I need to multiply this row by what to eliminate this?
Or 5.
Perfect. So which row again are we using now? Of course, that's the correct order. First I use row 1, then I will use row 2, and at the end I use row 3. So row 3 will be multiplied by something and added to row 1, and row 3 multiplied by something and added to row 2. So one more time, what do I multiply it by to eliminate the -5? Very good. What do I multiply by to eliminate the 2? Good. And this will be the final step. Which row do I copy? I'm sorry, I should have asked before writing it. Which row do I copy? It will not change because I'm using it.
3.
Of course. Because if I destroy row 3, I will never solve. Okay, let's do it together. 1 times 5 minus 5. 1 times 5 minus 3. 1 times -2 plus 2. 1 times -2 plus 1.
-1.
So we know the solution, assuming it's correct, because a tiny, tiny error destroys everything. It appears that the solution is 2, -1, 1. Do I know that for sure? Absolutely not. I go back 15 pages earlier, but it's not going to take this long. You'll see. And I also write very big. So I'm checking 2, -1, 1. 2, -1, 1. 2, -1, 1. 2, -1, 1. Ready? 2 minus 2 is 0. Negative 1 equals negative 1. Lucky so far. 2 plus 1 is 3, plus 1 is 4. Yes. 2 minus 1 is 1. 1 minus 3 is negative 2. So now I can say indeed, yes. I checked. And no one can find another solution. This is it.
I don't like Rubik's Cubes.
Say it again.
I don't like Rubik's Cubes. This is like a Rubik's Cube.
Well,
I'm just not good at Rubik's Cubes. So. Just gonna learn.
you will be very good at this. In the next week, that's what you're going to do.
Sadness.
Eat turkey. Eat turkey and do this. Okay, ready? Let's work on another problem. Ready? Yes, no?
Yes.
Okay.
Is this gonna be on the upcoming test?
Yes, and the final.
Okay.
Yes. Okay, so let's choose another. Let's say 20. Yeah, 23. I have no idea. So x plus 3y equals 0. X plus y plus z equals 1. And I said 23, right? Am I copying 23? Yes, I think I am. And 3x minus y minus z equals 11. Yes. Is the system arrayed correctly?
Yes.
Correct. Very good. We don't need anything else but directly the augmented matrix. Can anyone give us the augmented matrix? So really we cut off 10 minutes from the whole thing. By columns.
1,
1, 1, 3. 3, 1, negative 1. 0.
Perfect.
1, 1, negative 1.
That's it. We start the method. We got lucky. There is a 1 in here. We're going to use it to eliminate this and this. Obviously, I have to use row 1. What quantity do I need for eliminating the 1 in row 2? Perfect. What quantity do I need to eliminate the 3 in row 3? Very good. Awesome. Are you with me, everyone? Which row do I copy because it cannot change? I'm using it.
row 1.
Exactly. Very good. So 1 times negative 1 plus 1. 3 times negative 1 plus 1. Very good. 0 times negative 1 plus 1. 0 times negative 1 plus 1. 1 times negative 3 plus 3. 3 times negative 3 minus 1. Very good. 0 times negative 3 minus 1. 0 times negative 3 plus 11. Ugly. Because we have no choice. But divide this row by and we will have to use or work with fractions. One, 3, 0, 0, 0, 1, negative 1/2, negative 1/2, 0, negative 10, negative 1, 11. In this case, we have no choice. What did we accomplish? This is what I have so far. 1, 2, 3, 4. I have to use row 2 to eliminate the 3 and use row 2 to eliminate the negative 10. So row 2 multiplied plus row 1 and row 2 multiplied plus row 3. What do I multiply row 2 by to eliminate the 3? Yes,
-3.
Perfect. What do I multiply row 1 by to eliminate the negative 10? Very good. Which row do I copy? Because I know it cannot change because I'm using it. Perfect. 0, 1, negative 1/2, negative 1/2. And of course, the 1, 0 cannot change. Otherwise, I'm going backwards. Together. 1 times negative 3 plus 3. Ugly. Negative 1/2 minus 3, it's positive 3/2 plus 0. Same thing here. Negative 1/2 times negative 3 is 3/2 plus 0, 3/2. One times 10 minus 10. Perfect. Negative 1/2 times 10. Perfect. Negative 5 minus 1. Very good. Awesome. Negative 1/2 times 10. Negative 5 plus 11. It's right? Negative 5 plus. Okay, very good. What did we accomplish? A lot. Where am I now? Divided by? Awesome. 1, 0, 3/2, 3/2, 0, 1, negative 1/2, negative 1/2, and 0, 0, 1, negative 1. Which row I use now to eliminate the negative 1/2 and the 3/2? It has to be the last one, yes. Plus row 1 and row 3 multiplied by something and add it to row 2. Final step. What do I multiply by 1 by to eliminate 3/2? Negative 3/2. What do I multiply 1 by to eliminate negative 1/2? 1/2. Perfect. Okay, very last step. Promise. Okay. Which row do I copy? Because I'm using it. Yes. And of course I can copy these. If I mess this up, I'm going backwards and I'm not going to solve. Okay. 1 times negative 3/2 plus 3/2. Negative 1 times negative 3/2. Positive 3/2 plus 3/2. 3 over 2 plus 3 over 2 is 6 over 2, which is 1 times 1/2 minus 1/2. Negative 1 times 1/2 is negative 1/2 minus 1/2 is it appears so easy to make an error, but it appears that the solution is
3 -1 -1.
have no clue. So this one took us like 3 minutes. The first one, what? 20. Okay. So where is my system? Here it is. So I'm checking 3, negative 1, negative 1. Okay. 3 minus 3. 3 minus 1 is 2. 2 minus 1 is 1. 9 plus 1 is 10. Plus 1, 11. Because this is positive, this is positive, this is 9. So then I will say yes. And this is the method called Gauss-Jordan for solving systems of 3 linear equations in 3 variables. Yes, we have other methods also, elimination, substitution, inverse matrix, and so on and so forth. But this was Gauss-Jordan.
Substitution and elimination always work too, right?
Yes, but more difficult, especially substitution. So with the elimination, you will take two equations and eliminate one variable, and then create an equation with two variables, and then pair two other equations, eliminate the same variable, and create a system of 2 by 2, and solve that system, and then come back and solve for the third variable.
When we were doing those, we were only doing 2 equations at a time, right? Not 3.
In the chapter 5, yes, yes.
So you used this
So this one can get hairy, right? Can be, especially with fractions, but most probably will take less time than using elimination on a 3 by 3.
But only if you have 1 and 2.
The elimination.
I'm saying if you have more than 2 equations,
You can have more than 2 equations. The other methods work, but it will take a little bit longer. And we also have other methods. But we don't present, we only present one method here, but I can show you. But the problem is that the inverse matrix will not work unless the system has solutions. So we have other methods. We have the Cramer's rule, there is another method. There is inverse matrix, which is another method. We have Gauss-Jordan, which is another method. Your book also presents the Gaussian elimination, which is only half of this method. I chose to present the entire method, but if you want to use Gaussian elimination, I'm fine with that. The Gaussian elimination does not determine the zeros above. So you determine z, and then you go back and determine y. And you go back and determine with x, with y and z, you determine x. I chose to show the entire method because if I know how to get these zeros, I will know how to get those zeros. And then why stop in the middle? But I accept the other method as well. Okay, so I think we should look now at the last section, which is 8.1, and then we'll come back for more problems. 8.1 is probably the easiest of all. Again, at first it will look a little bit weird, but you will see. So yes or no?